the way to think about it is this. Given any two vectors A and B, the projection of B along A is B hat, and there are many vectors along A, an infinite number of vectors. We have to choose the right one. How do you choose the right one? So in order to choose the right one, we define the perpendicular distance that we saw here, the perpendicular distance here, and choose the one with the lowest perpendicular distance. That's what we want to do. And the lowest will happen when that perpendicular vector is perpendicular to A. So that's what we want to do. So the projection of B is in the same direction as A. So it's a scale version of A. So let's call that scaling factor X. So the error now is what? It would be minus B hat, and that is the error. Okay, so we'll call that the error vector, and that is B minus B hat. That will give me B hat is equal to B minus the error vector. That is XA, some scale version of A, because B hat is along the direction of A. For my own purposes, instead of writing it XA, I'm going to write it AX, which I'm allowed to do because scalar multiplication is commutative. So let me show this to you using better graphics. I have A there, that is a line that defines the subspace of A, and then I have a vector B there, and I have B hat, and among all the vectors along A in the subspace of A, I'm choosing this particular one because that perpendicular vector is the smallest possible one. So that is the vector. Since all our vectors start from the origin, I move it to the origin. And I can say that B is actually B hat plus the error. So B hat, and move E to the tip of B hat, and I'll reach B. So B is B hat plus E, which means B hat is B minus E, and that has to be along the direction of A, which means there's some scaling factor X which will say that B hat or B minus E is equal to AX. So that's all I want to say. By construction, the error vector E is orthogonal to A. It has to be. That will be the vector that is closest to B along the direction of A. That will happen only when E is orthogonal to A. If E is not orthogonal, if E is in some other direction, then that length is obviously not the smallest. This one would be the smallest because that is the orthogonal one. So it is orthogonal to A. What does that mean? That means A transpose E has to be 0. Now error added to the projection vector B hat is B because that is the error. So B is equal to B hat plus the error vector E. So E is B minus B hat. So E is B minus B hat. That means A transpose times B minus B hat, that is the error, that is equal to 0. So since the projection B hat is along the direction of A, we call it A times X hat. X hat being the right scaling factor, so that I get B hat. So I can write B hat is equal to AX hat, or A transpose B minus AX hat is equal to 0. I know that this becomes kind of sounds like I'm going around in circles. I'm just guiding you through a series of steps that will take me to the right answer very soon. So what I'm saying is A transpose times an error vector is equal to 0. A transpose dotted with an error vector equal to 0 because A transpose is orthogonal to the error vector, and the error vector is the original vector that I want to project minus the projection. So that is the definition of the error, and the projection has to be along the direction of A. So it's a scale version of A, and the scaling factor is X hat. And if I can find X hat, then I'm done. But I have an equation right here that will give me X hat. So if you look at this guy here, you can actually see something similar, remnants of our favorite equation, AX equal to B. It is already there. Everything somehow comes back to AX equal to B in our course. So let's look at it again. So I have A transpose, that is a dot product of A with the error vector, B minus the projection, which is A X hat, is equal to 0. So if I just expand it and move this guy to the right hand side, I get A transpose B is equal to A transpose A X hat. A transpose B is X hat A transpose A. Okay, so I can get X hat right there. So X hat is just a number, and A transpose A is a dot product is actually the square of the norm of A, so that is just a number also. So X hat is A transpose B, which is a dot product divided by that guy. Now the projection I want is not just the number X hat, I actually want the vector B hat, meaning I want to take X hat and multiply that by A. So B hat is actually A times X hat. So B is equal to X hat, which is here, that is the same as this, times A, and then I can move it around. This guy is actually just a number. So I can move that to the other side of A. And then I can move this to the numerator. I get A transpose divided by A transpose A times B. Again, I get this operator. That is a matrix. A transpose is an n by n matrix. And that is the operator that will take me from a vector to its projection onto the direction of A. So now, how could I write these things? Because I have associative property of matrix multiplication. I can group them in any way I want. Can do any multiplication first. A transpose B is the same as A times A transpose B, and I can basically group them in any way I want. Any grouping is valid. And if there is a scalar multiplication, I can always move that scalar around. So all those things are fine. So we came up with the projection as A transpose divided by A transpose A. So A transpose A below is just a number. So ignore that for a minute and then look at the shape of A transpose. That's a matrix because A is n rows and one column. That's a vector. A transpose then is one row and n columns. A transpose is an n by n matrix. The projection matrix, if you define that as A transpose divided by A transpose A, then I get a matrix, n by n matrix, but what's its rank? Its rank is 1. So let's take an example. A is a column vector 1, 2, 3. So A transpose is 1, 2, 3 in a row. It's a row matrix. And if I do the multiplication by the row picture, the rows of the product are linear combinations of the rows of my matrix on the right, scaled by the weights in my matrix on the left. So the first row is a 1, 2, 3. So 1 times 1, 1 times 2, 1 times 3. The second row is 2 times 1, 2 times 2, 2 times 3. So 2, 4, 6. The third one is 3, 6, 9. So you can see that the matrix, the second row is just twice the first row. The third row is 3 times the first row. They are all basically linear combinations of scale versions of one row. It has to be because we have only one row. So there is only one linearly independent row. And if I actually do Gaussian elimination on this one, I'll take twice the first row, subtract from the second one to get all zeros. 3 times the first row, subtract from the third row to get all zeros. So 2 0 rows, only one row with pivot. So rank is 1. Also, A transpose, if I transpose the whole thing, I get A transpose. It's symmetric. You can actually see it here. So 2 and 2 here, 3 and 3 here, 6 and 6. So it's symmetric. It has to be. So some properties of the projection matrix, symmetric and rank 1. So that is my projection matrix again. So given any vector B, a blue vector, the projection is already along A. But if I do it twice, if I project the projection, what will happen? The projection is already along A. If I project it again, since it's already along A, it's not going to change. What that means is that if I take the square of the projection operator, or rather, if I apply the projection operator twice on a vector, it is the same as applying it once. So that you can see by just multiplying P by P. So A transpose, A transpose, A transpose, A transpose, A transpose, A. If I do that, and then if I do some kind of grouping, I can see that the purple part will just cancel off, and I'll get P square is equal to P. It doesn't matter how many times you apply it, you always get the same answer. Multiple applications don't actually change the answer. And I think the name for such matrices is actually idempotent. P square is equal to P implies that P is idempotent. So if I look at it, does it imply that, can you cancel P on both sides and say P is equal to I? P square is equal to P. Then can I write P square times P inverse is equal to P times P inverse, right multiplying by P inverse, and this would imply P is equal to I. Obviously I shouldn't be able to do this, and can you see the reason why I should not be able to do this? P has no inverse, and that is true. P inverse does not exist. It is not invertible. Why is it that it is not invertible? Now P is a square matrix, A transpose. So this is in R n by n. So it is a square matrix. It is not full rank. P is a rank 1. So it is not a full rank matrix. But can you see a situation where P inverse does exist? Rank 1 is not full rank as long as n is greater than 1. But if n is equal to 1, if you're working with a one-dimensional space, just real numbers, then P inverse does exist because P is just a scalar and P inverse is just a reciprocal. Linear algebra is actually wonderfully consistent. Whatever kind of little inconsistency you try to find, you will always fail. I was trying to find an inconsistency saying that in one dimension, maybe it fails, it doesn't. So the reason is basically that it is rank 1, but the reason why it is rank 1 is that it actually destroys information. When you project a vector onto another vector, you're actually throwing away some part of the information. What will happen if I take a vector, project it, and if I double the vector? If you double the vector b, obviously the projection will double. What happens if you double the vector a? The projection should not change, because a, the purpose of having a vector a is just to define the line, define the subspace, define the direction. That means regardless of what the length of a is, the projection will not change. That means the projection operator cannot change. So let's verify that. So suppose I double a, what happens is that wherever I see a in P, I'll just put 2a, and we'll just have a factor 2 times 2 in the numerator and 2 times 2 in the denominator. That will give me just p. That will just cancel off. And the inversion of p cannot be done because we lost information in making the projection, which means multiple vectors b can actually give you the same projection b hat. And we saw that it is actually a rank 1 matrix. And the last thing I want to ask you is p a linear operation? Multiplying b with p, it will give me the projection, but is it linear? Yes, it is. A multiplication by a matrix is always a linear operation. That is the definition of linearity, because we started, remember, that's why I asked you to go back and look at the early chapters once in a while, because we came up with the concept of a vector and a matrix because we started with the notion of linearity. So it is a linear operation. Now the question is, how do you distinguish between P, the permutation matrix, and P, the projection matrix? Well, basically that is a chiding on using the same symbol for both these things. But since both these words, permutation and projection, begin with the letter P, it's not my fault. It is a fault of English language. And you will distinguish it, will differentiate between those two using the context. So actually, in order to make sure that P is a linear operation, you can actually do the tests of linearity if you want to. You can scale and sum, etc. and homogeneity, additivity, those conditions. Multiple vectors can give you the same projection. If I have a B, projection is like shining light onto the tip of B in a direction that is perpendicular to A. So I get that as my B hat. But any other vector whose tip is on that perpendicular line will give me the same B hat. Okay, several vectors will have the same projection B hat, which means given a B hat, I cannot really tell which B it came from. I cannot reverse the operation. So P is a singular matrix by its very nature, because multiple input vectors will give you the same projection. What's the column space of the projection matrix P? Taking a projection of a matrix of a vector P is multiplying that vector on the left by P, which means you're taking the linear combination of the columns of P. So this multiplication here, we're taking the linear combinations of the columns of P. So the projection, which is P times B, will be in the column space of P. So the product has to be in the column space of P. But all products, regardless of what B is, will be in the direction of A. Remember, that is what projection is. Projection operation is an operation that will take a B to the direction of A. So the column space of P is actually just a line that is defined by A, because the projection has to be along the direction of A. That is obvious because that is the definition of projection. But this multiplication basically says that the product has to be in the column space of P. That means the column space is actually just a line that is defined by A. So that is an interesting property. And the dimension of the column space is the rank of P. And we saw that P is a rank 1 matrix. So there is only one line that is in the column space of P. Column space of P, if you were to write it, but you can see it by looking at the matrix. I started with an A as an example. 1, 2, 3, remember? 1, 2, 3. And I had A transpose, which was 1, 2, 3. Then A transpose, which is the numerator of P. This divided by some S. So ignore the S for now. So this is like 1, 2, 3, 2, 4, 6, 3, 6, 9. So this is a matrix that we got. And we see that this is actually symmetric. And the first column here, this column here, is actually just A. And all of the columns are this is 2A and this is 3A. And the column space is actually just linear combinations of the columns, which means scalar multiples of A. So just one line. The column space of P is a scalar multiples of A. So the rank of P is 1, it's a rank 1 matrix. So if you were to store a rank 1 matrix if you want to store an n by n matrix, a general n by n matrix, a full rank matrix, you need n square storing locations. So if it is a 100 by 100 matrix, you need 10,000 floating point locations in the memory. But if you know that that A is actually rank 1, then all you need would be 100 numbers to store one row, and then 100 more numbers to store the scaling factors for all of the rows. So it is like 200 floating point locations rather than 10,000. And similarly, if you were to do any kind of operations on this matrix, there will be corresponding kinds of savings if you were to write those programs carefully. If you know that something is a rank 1, you should be able to use that.